All right. The last thing I want to talk to you about um, today or in these videos, such that you're ready for assignment one, is the topic of non-regular languages. So, unsurprisingly, not all languages are in fact regular, right? So it would be pretty surprising if all languages, so then all language membership problems, so in other words, all decision problems could be decided using a finite amount of memory. That'd be pretty surprising because, for instance, if you took the language, something like ANBN, where N was just any natural number, if you want to design a DFA which accepts strings in L and only in L, the DFA kind of has to remember an arbitrary number of A's before switching to reading B's, right? So, the way that someone would probably try to design a DFA or an FA to accept this language would be something like, I have my start state, and then epsilon, that's cool. AB, that's also cool. AA, BB, that's also cool. But quickly you start to see that there's no sort of end to this NFA, and it would just keep growing and growing. You would need to have an infinite number of states to be able to accept this language because you need to precisely remember the number of A's you've seen so that you can check them with the number of B's. And that does not intuitively sound like something a DFA could do because DFAs and NFAs and NFAs with epsilon transitions, they're finite automata. They only have a finite number of states. In other words, they can only contain a finite amount of memory. And so here it looks like you need an arbitrarily large amount of memory, right? There's no sort of cap on how much you should be able to remember. There's no restriction, right? And so, of course, the sort of way of sort of driving this point even further is, if you had a very similar language like L sub 330, where L sub 330 was kind of like a subset of L, except that it only had strings up to n at most 330. Well, then this, right, this is definitely regular because this language is finite, right? This language is finite. So essentially you can just you can hard code all of the strings from L sub 330 into an FA, and you'll accept all and only all the ones in L sub 330. And so this should sort of drive the point home that um, something like this cannot really be accepted by an FA because this can definitely be accepted by an FA because you have sort of a finite number of things to accept. But because L is infinite and L could be infinite and still regular, but because L is infinite and you have to remember an arbitrarily long sequence, which requires sort of having hard coding all of the possibilities from from L. And so having sort of what would look like an infinite FA, that's not something that's possible. And so that's why this is not regular, right? So this is the intuitive argument. So this is the intuitive argument. But now, this is a theory class. So how do we prove it formally? So how do we prove it formally? There's, I would say, three main ways of proving that a language is regular. The first one is with the pumping lemma. The second one is with the Myhill-Nerode theorem. And the third one is with closure properties. I'm only going to do the pumping lemma because I think that's the only one you've really seen in terms of how to show that a language is not regular. So to do this more formally, you can use the pumping lemma. So essentially, in a nutshell, what the pumping lemma is it's a necessary condition for a language to be regular. In other words, if L is regular, then we have a lemma which tells us that the conditions of the pumping lemma are satisfied. Okay, well, how does this help us in showing that something is not regular? Well, you can just take the contrapositive, right? So you can just say you negate, you show that a language does not satisfy the conditions of the pumping lemma, and so therefore by contrapositive, it cannot be regular. Okay. So now, what does the pumping lemma actually say? What are the conditions in the pumping lemma? I'm not going to prove it. I'm just going to state the conditions. So the pumping lemma conditions are the following. Given, some non-empty alphabet and some language in sigma star, then what the conditions of the pumping lemma say is that there exists some pumping length P, which is a natural number, which, just to be safe, is strictly greater than 0, such that, so this dot here just means such that, for every string in L, if that string is greater or equal to P, then we have that there is a decomposition XYZ for which W is that decomposition XYZ, and the length of XY is at most P, and the length of Y is at least 1, right? So we have this decomposition for every possible string in the language with length at least P, where P is some natural numbers that we know exists. And the special thing about this decomposition is that for every natural number, in this case, natural numbers in computer science contain 0, but I'll just specify I greater or equal to 0. For every natural number, if you pump the middle part of that decomposition, so the Y, any number of times, so either 0 times, meaning you take it away, or I greater or equal to 1 time, so meaning you replicate it, then, so the string yi, which is just taking yi and replicating it, taking y and replicating it I times, then this is necessarily in L. Okay? So that's what the pumping lemma, the conditions of the pumping lemma say. Now, how do I do this? How do I use this to show that something is not regular? Like I just said, you have to negate it, right? So I'm not going to explain why exactly this becomes the negation of the pumping lemma. Hopefully you've done that in lecture. I'm just going to negate it for you. So if you negate this thing, right, then existentials become for alls, and for alls become existentials. So the negation then becomes, I'm just going to do it here so I don't have to rewrite it. For every P, for every pumping length P, there is some string W where for any decomposition of that string, I can find an I for which X, Y, I, Z is not in L. Okay? So that's the negation of the pumping lemma conditions. And if I show that for some language L, this statement holds, then that means that the contrapositive is true. That means that the premise in the contrapositive is true, and so the conclusion in the contrapositive is also true, namely L is not regular. Okay, so this is probably still very abstract. So how do I actually use this? How do we use this? Okay, so essentially, I very much like this way of explaining the pumping lemma and how to use it. Essentially, what's going on is you're playing a game. Okay, so you play a game where you play the role of the existential quantifier, And your opponent is the for all quantifier, okay? The universal quantifier. And so you're playing this game where at your turn, right? At your turn, you make a move. You sort of pick some string or some integer. And at the opponent's turn, they do something. And you have, of course, no control over your opponent, right? That wouldn't be a very fair game if you were playing chess and you could sort of hold the hand of your opponent, right? So you cannot force your opponent to pick any kind of, in this case, pumping length or decomposition, right? All you can do is sort of respond to their move by picking a string and then by picking some I, where WI is not in L, right? So that's how you win the game, right? You win the game. So what's the point? What's the point of this game? It's to win, right? So you want to win, right? How do you win, right? How do you win? You need to find a winning strategy, i.e. a way of satisfying the negation of the pumping lemma conditions. Find a winning strategy, where you don't assume anything about your opponent, where opponent is free to play any move. Okay, but this is the general idea. This is what you want to do. So let me illustrate this. Oh boy, let me illustrate this. Still, I thought I had deleted this. Clear page. Oh, what the heck? Okay. So let me illustrate this with an example. Sorry about that. So this example is show with the pumping lemma. Show with the pumping lemma that L A2N, sorry, Bn is not regular. So intuitively, this is not regular because, it's not easier. It's not any easier than A and Bn. It's, somewhat harder, right? Because now, not only do you have to remember the number of A's, you have to remember twice the number of A's. So it's definitely not easier, and it seems like it's just as difficult. So it doesn't seem like an FA, any amount of finite number of states could allow you to sort of correctly accept all the strings in L and only all the strings in L. You definitely have like a false negative or a false positive. Okay, so now let's play this game, right? Let's play this game. The for all opponent, right? My opponent that plays the for all. I don't control what they do. Their move is just to pick some pumping length P, right? So that's what they do. I don't assume what P is, right? I don't assume what P is. So opponent picks P. The only thing I can assume is that they're following the rules, right? Meaning that P is an N and P is strictly greater than 0. Okay, so the opponent follows the rules, otherwise they would be cheating. That's not fair. Now it's my turn, right? Now it's my turn. So now it's the existential quantifier's turn. So what do I need to do? I need to pick a string W and L where the length of W is P. Now, there's an infinite number of strings I could pick. The strategy, right? So the strategy here, is to think 2 steps ahead, right? You want to think 2 steps ahead because you want to think, okay, if I pick this string, my opponent is going to be able to decompose it any way they want. And then I'm going to have to show that for any of those decompositions, if I'm able to pump up or down with some I, and that pump is going to lead me to a string that's not in L. So that's the sort of key idea, okay? So what could be one possible choice of W? Well, I could say maybe W is AP BP over 2, right? Why? Because, my opponent is going to decompose, right? My opponent is going to get this string, and then the decomposition is going to be XYZ, where XY, right, the length of XY is at most P. So then I know that my opponent is going to decompose, and the decomposition is going to have XY only among A's. So then I'll know that Y is just a bunch of A's. And then I can pump up, right? Because if I pump up, then I get something like A power P plus K. And that's definitely bigger than twice the number of B's, right? That's the general strategy. However, this choice of string is actually not ideal, right? It sounds like it's, pretty plausible that this strategy might work, but this is not ideal. Why? Because in this case, what if P, right? Well, what if P is odd? Then I have B power P over 2, where P over 2 is no longer a natural number. So what does it mean to, power a B to the 2.5? Does it mean like I cut the B into 2? No, right? There's no such thing. So that means in that case, the string W is not going to be. So in that case, W will not be in L. And that's a problem, right? Because I also have to respect the rules of the game. And the rules of the game is that I pick a W that's in L, right? So that's not good, right? Well, let's see. Let's try to fix this by saying, well, suppose, right? Let's use the same choice of string. But now I say I enforce P is even. Then that fixes the problem of this not being an L, right? Because I say, well, I just force P to never be odd. It always has to be even. But again, that's a problem. That's not a problem because you're not satisfying W and L. It's a problem because now what you've implicitly done is you've actually forced the hand, right? You've forced the hand of the opponent, and you've told them that they must pick a P that is even, right? And you can't do that, right? Imagine I'm playing chess with someone else, and I tell them, okay, you do that exact move. Well, clearly that's not a fair strategy, right? So remember, I need a winning strategy that is fair and that respects the rules. So again, this is not good. This is not good. You cannot. And you know what? This warrants caps because this is a very common error, okay? This is a very common error. So try not to make it. Cannot force for all you pick P even. Okay. So then what I need to do, right, is I kind of need to be a bit clever. And I need to say, well, suppose I got a P, I need to make A power something even, right? Because it has to look like 2n. And then I have to have some number of B's where the number of B's is half the number of A's. Well, in this case, I can really just use the sort of definition of L, and I can just say, let's pick W is A to P and BP, right? So this does not assume, right? This does not assume that P is odd or even, and it's definitely an L. So that's great. I'm very happy. Now, also, it does seem like because this argument here with P worked, it's probably also going to work with 2P. Because now the for all player picks a decomposition. W, X, Y, Z. And of course, remember, you can't force the opponent to pick a specific decomposition, but you know that they're sort of constrained in the moves they can make. Namely, XY is at most P and Y is at least 1, right? So you know that you're assuming, and this is a fine assumption to make, that they're respecting the rules of the game. Meaning that you know that the decomposition XYZ, well, you're going to have W is a bunch of A's, 2P times, and then a bunch of B's P times. But then if I'm decomposing this into X, Y, Z, then XY is at most of length P. So meaning that it's at most A power P, right? So what that tells me is that therefore Y is just a sequence of A's, right? Y is just somewhere in here, where it's just some sequence of A's, let's call it KA's, okay, where K is definitely more than one, and it's at most P. Okay. And this is great. This is great for me because now if it comes back to my turn, right, all I need to do is I need to pick an I where WI is no longer in L. But now the choice is anything except for I is equal to 1, basically. So if I pick I is equal to 0, then W0 is XZ. And what this is doing is it's saying, well, take these KAs and take them out of the A power 2P. So then that's A power 2P minus those KAs, and then B power P, okay? And this is not in L, right? This is not in L. Why? Because the definition for a string to be in L is that the number of A's should be twice the number of B's, but 2 times P is greater or equal to 2 times P minus 1 is strictly greater, right? Strictly greater than 2 times P minus 1, and this is greater or equal to 2P minus K because of this inequality here, okay? If I picked I was equal to 2, then I would get W2 is X, Y, Y, Z. And now what's going on is, this is why you have the name pumping lemma. I sort of inject or I pump an extra KAs. You can imagine just inserting an extra KAs here. Whoops. Okay, it's okay, we're almost done. An extra KAs here. And so what that means is I have A power 2P plus K, B power P. And this is again not in L, because in this case, 2 power P, 2P plus K is strictly, or is greater or equal to 2P plus 1, and that's strictly greater than 2P, right? Which is what this should be, right? So this should be 2P, but in fact, it's strictly greater, right? So it can't possibly be equal to it. So in this case, I could have used any I except for 1, and it would have worked. Sometimes you have to be a bit more careful. Like for instance, if it was something like the number of A's is greater or equal to twice the number of B's, right? The number of A's is greater or equal to twice the number of B's, or the number of A's is maybe strictly less than twice the number of B's. Then you have to be more careful, and it depends whether, and you have to think sort of a bit more carefully when you choose the I, whether you should pump up or down. Okay, great. So hopefully this is clear. Now let's do another example. So let's do another example where here I'm not telling you to show that a language is regular or not regular. Instead, I'm asking, is L XWX, where W is in A or B star, regular? Right, so is this language regular? This language is essentially a string that can be represented by some string at the beginning, which is exactly the same as the string at the end. And then in the middle, you have the string W, right? So any string. Well, I think the sort of natural intuition would be, well, I have X and X at the beginning and at the end. So what that tells me is that the FA, if I were to design it, would have to sort of remember the X at the beginning of the string and then go through the W and then check that the final part of the string is the same as the beginning, right? And because X can be as big as you want or as small as you want, the number of states you're going to need for an FA to do that is infinite, right? Because you X can be anything, right? It can be any arbitrary string, right? So I think intuitively and naturally, I would probably say, well, it's not regular. Yeah. Not regular. It's getting late. It's not regular. Okay. So then again, let's just use the pumping lemma to see how this can work. So my opponent, they pick P. Then I pick a string W. So here, let's see. I need a string that's in L, right? Remember, that's the first requirement. And I need a string that when I pump up or down, I can at least find, or essentially I can find a pump that allows me to say that WI is not in L. So an easy thing is probably, you have AP and AP at the beginning and at the end, and you say, well, this is X. And then W can be anything, right? So let's just say W is B, okay? And this is probably going to work because if I pump up, right? If I pump up, so I'm like sort of imagining a few steps ahead. If I pump up by 1, then I'll get AP plus K, B, AP, right? And then, of course, I break this assumption that I have X here and X here. These are clearly not the same. Okay, so let's try that. Let's try that out. So let's say you have my for all player, right? My for all player, or in other words, my opponent, they decompose the string W, right? So they decompose the string W, which is a bunch of A's. Oops. Then B with a bunch more A's. Okay. And then because they have to play by the rules of the game, right? They're sort of decomposing this into X, Y, Z. And XY is at most APs, right? A power P. So because of this restriction, XY is at most PAs, and Y has to be at least one A, right? So in other words, that means that Y is AK, where K is between 1 and P. Okay, so it looks like this intuition here might work. So now it's my turn, right? It's my turn, and let's do what I said. Here, let's pick I is equal to 2. And then W2 is X, Y2, Z. So that's X, Y, Y, Z. So essentially, you take maybe these AKs, and now you inject an extra sequence of AKs. So what you get then is you get AP plus K, B, AP. Okay, so now I just have to quickly show that this is not in L. But there's a bit of a problem, isn't there? Right? Hopefully you've already spotted it. The problem is if I look at this a bit more carefully, this is the string, right? This is one way of representing the string. And now it kind of looks like this is an L, right? So, this is X, and this is X, and then this is W. So it looks like this is in L, okay? And usually when this happens, your pumping lemma fails. It's two things, really. There's only three things that can happen. The first thing is the pump was wrong, right? That's probably not the case because, if I pump down, then if I pump down, right? If I pump down, then in an extreme scenario, right? So so what I'll get is a power p minus k, b a power p. So I still have some a's at the beginning and some a's at the end. And it's likely that I have some way of having the same number of a's at the beginning and at the end. So the most extreme case would be if my opponent had picked k to be p, right? If k was p, then so if k was p, if, right, k was p, it's not necessarily the case, then I would get something like epsilon b ap. So now, how can this be in the language? Well, you always have to be careful about the empty string, right? X and Y can be the empty string because they're in AB star. So X can be the empty string, right? You can have epsilon here and epsilon here, meaning that, you can take this epsilon and you can say this is X, and then have X, take an extra epsilon here and say this is X, and say the middle is W. So again, the pump, it wasn't a problem with the pump. And really, it seems to be a problem with the language because the only other thing, right, so the first thing was the pump was wrong. Doesn't look like that's the case. The other thing is maybe the string was wrong. I'm starting to doubt that, right? So the only other possibility is that, in fact, this language was, well, okay, there's an extra possibility. I won't talk about it. The most likely thing that's to be the case is that L was in fact regular, right? So that's the third possibility. So let's see if that's really the case. So how could this be? How, oh, how? Well, I'm starting to think that it has to do with this kind of epsilon string, because now consider any string, right? So consider the string A, B, B, A, B. This doesn't seem like it would match X, Y, X because, this, or at least let's do it like this. Yeah, let's do this thing. Something like this, right? So, you take the start of this string, AB, there's no AB here, ABB, that's BBB. But you can always sort of, if it doesn't look like there's a greater or equal to 1 match for X, you can always sort of use the sort of epsilon trick, right? So you can say, well, epsilon X is just X, right? So I'm allowed to just concatenate an extra epsilon. The same thing for appending an epsilon. And I can definitely say that X can be epsilon here and here. And W, right, I'm saying that W is any string over AB. Aha. So it turns out that this language was actually secretly A or B star, which is definitely regular, right? This language is definitely regular. Here's a DFA that accepts it, right? So in fact, L was regular. Okay. So like I said, that's typically the three things you have to consider if your pumping lemma fails. Either you picked the wrong I, or the string you picked to begin with was not the right one, or actually you chose the incorrect decision. There's kind of an extra case. So the fourth case is it's possible for a language to not be regular, but to satisfy the pumping lemma. But those are very rare. And unless we're trying to be extremely nasty and trick you, that's probably not going to be the case. Okay. Because notice notice what I just said. Yeah. So notice this is a necessary condition, right? So if you negate the premise here, if you say L is not regular, it does not necessarily mean, right? If you have P, then Q, then not P, then not Q is not necessarily true, right? But that's a pretty rare case, to be honest. Okay, so the last thing I want to talk about is, you could have actually slightly tweaked this example to make it actually truly not regular. So if you had done something like L is XWX, where you have the same thing, sigma is AB. So the same start of the set builder notation, except that now I have this additional restriction that the length of W is 1, right? Then in that case, right, if I have a non-zero, well, I'm going to have a string of non-zero length. And if I have a string of non-zero length, then W has to be exactly of length 1. So, in this case, it'd have to be maybe this thing. In which case, I can no longer use this epsilon trick, right? Because I can't say X is epsilon and X is epsilon, because then that would mean that W has length greater than 1. So in that case, right, it does seem like I have to read X, remember it, then at some point guess that I'm reading W, and then check that the rest of the string I'm reading is exactly equal to X, right? And that definitely sounds like something an FA could not do, right? It can't sort of remember every possible X. So I'm going to do this pumping lemma quickly, because it's also getting late. So your opponent picks a natural number, which is greater than 0. Then I pick, turns out if I use AP, B, AP in this case, then it's going to work out, because my opponent is going to say, well, I'm going to decompose here, X, Y, and then Z. Again, in this case, Y has to be A power K, where K is between 1 and P. Okay. But now, right, if I pump up, right, and I get W2, so, these are the exact same steps as before. Then let's think about what W could be, right? So W could be in the A's, right? In which case, if it's in the A's, so let's expand this. If KA is here, PA is here, then we have B, PA is here. Okay. So what could the W be, right? So let's see. I mean, whoops. It can be here, but that's definitely not going to work out, because then X would be the empty string, and then X would be this as well, which, then X would not be equal to itself. So essentially what your opponent is trying to look for is, can I find a W where actually this, can I find like a way of satisfying the definition of L? Because then that means that the pump doesn't defeat me, right? Doesn't defeat the opponent. So if I go further into the string, like here, then I have some number of A's, and then the rest of the string on the right is A's, and then a B, right? So that's not good. And that's true for any sort of choice of W here. If I pick W as B, then, that doesn't work, because X has length P plus K here and length P here. And then if I pick W here, then on the right-hand side, X has only A's, and then on the left-hand side, X has a B, right? And so that means that X is not equal to itself, which is, of course, not possible. So indeed, W2 is not an L, and so therefore L is indeed not regular. Okay, so I hope this was helpful for doing the assignment, and yeah, I'll see you next time.